Agentic era presents a fundamental breakthrough in understanding AI representation spaces. Researchers from the University of Chicago and INSEAD have unlocked Bregman duality. This shift moves beyond traditional linear assumptions within the representation space. The core innovation is dual steering for zero-leakage concept control. This method manipulates representations in their natural geometric state. Empirical evidence confirms stability across both LLMs and vision systems. The system achieves an R-squared value greater than 0.98. It also maintains a convergence rate of big O of 1 over the square root of t. Most significantly, dual steering reduces concept leakage to approximately 0.01%. This framework provides a robust foundation for steering behavior without unintended side effects. The linear representation hypothesis serves as the current standard for AI models. This mechanism posits that high-level concepts correspond to specific directional vectors. Concepts like sentiment or gender are treated as coordinates in space. Researchers identify and manipulate these representation vectors labeled as lambda. The model assumes that lambda exists in a flat d-dimensional real space. This suggests that simple vector addition can reliably change model outputs. In practice, this linear approach often yields inconsistent and mixed results. Methods based on this standard remain brittle and prone to failure. Attempts to steer models often trigger catastrophic off-target effects. These unintended changes suggest the flat grid assumption is fundamentally flawed. This creates a significant bottleneck for achieving stable and precise control. Current steering methods are based on the Euclidean illusion of flat geometry. Theory suggests a straight path from a source to a target with zero error. This standard approach follows the formula lambda t equals lambda 0 plus t times beta w. In reality, vectors encounter chaotic dispersion on a warped mountainous manifold. Multiple vectors deviate from the intended path, leading to high error rates. This phenomenon triggers detectable off-target effects and probability mass leakage. The researchers reveal a fundamental structural flaw in this linear mapping. Standard methods commit a mathematical type error by mixing different spaces. They naively add a linear dual space operator directly into the primal representation space. Because the geometry is nonlinear, these updates result in chaotic covariance. This mismatch explains why current directional vectors fail to provide precise control. Softmax distributions represent the core output layer of neural networks. They are often misunderstood as living in flat Euclidean space. Information geometry reveals these distributions inhabit a dually flat Bregman geometry. This intrinsic structure is defined by the Kullback-Leibler divergence. This divergence is mathematically equivalent to a Bregman divergence. The formula involves the function a of lambda. The divergence between p lambda and p prime lambda is explicitly defined. It equals a lambda prime minus a lambda. The gradient of a transposed is then multiplied by the difference in lambda and subtracted. This specific geometric structure aligns perfectly with how models produce behavior. It provides the exact language needed to track changes in representation space. This foundation allows for more precise control than linear approximations. Information geometry maps a single probability distribution across two linked spaces. On one side is the primal space, representing the context embedding lambda. On the other side is the dual space, labeled as phi. A bridge connects these two representations through a formal mapping. The dual coordinate phi is defined by the gradient of the potential function a of lambda. This transformation represents the mathematical expectation of gamma given lambda. In practical terms, this is the expectation over the unembedding vectors. While researchers usually work within the primal space, behavioral concepts are dual. Moving between these spaces allows for a deeper understanding of model behavior. This duality provides the necessary coordinates for more efficient representation steering. Mapping these expectations ensures changes align with the actual distribution of tokens. Primal and dual spaces exhibit fundamentally different interpolation mechanics. Primal interpolation uses the E-geodesic to minimize reverse KL divergence. This path effectively acts as a logical AND operator or intersection. In tests tracking tokens like Paris and Berlin, primal interpolation shows a sharp dip. The total probability mass collapses between the two target tokens during the transition. Dual interpolation instead uses the M-geodesic to minimize forward KL divergence. This path acts as a logical OR operator, creating a linear mixture. The resulting chart shows a smooth, constant transition of probability mass. Total confidence remains high as probability shifts from the first token to the second. These mechanics are demonstrated using specific queries about the capitals of France and Germany. Understanding this difference is critical for maintaining model confidence during steering. Dual coordinates provide the necessary linear mixture for stable concept transitions. The dual steering architecture represents a major departure from existing methods. Standard probes are typically injected into the primal space. This new innovation instead injects probes into the natural dual space. The system follows a linear path defined by phi of lambda t. This equals the initial state plus t times the steering vector beta w. By operating in the dual space, the architecture provides a mathematical guarantee. It allows for the modification of a specific target concept. Simultaneously, it minimizes unintended changes to all off-target concepts. This approach addresses the root cause of previous steering failures. It ensures that the model remains grounded in its original distribution. This precision is essential for building safe and controllable AI systems. Dual steering creates a more predictable relationship between vector changes and model behavior. Concept factorization is the theoretical driver behind the success of dual steering. This process compares an initial probability state, P0, with a steered state, P1. In this framework, target concepts like father or uncle are modified through counterfactual pairs. Direct probability shifts occur between these specific related tokens. Simultaneously, the system ensures zero probability drift for neutral outputs. Neutral tokens, such as the word friend, are held constant by a theoretical lock. This preservation is mathematically supported by the research team's Theorem 3. Dual steering identifies a unique minimizer on the distribution hyperplane. This point optimally preserves the entire off-target distribution, labeled PZ. The result is a surgical modification of targeted concepts without side effects. This achieves a level of precision that was previously considered impossible. It confirms that steering can be both deep and perfectly isolated. Transitioning this theoretical model to engineering presents a unique rank deficiency hurdle. The dual space phi is not infinite, but rather a bounded convex set. In some states, softmax distributions become highly concentrated on single tokens. This concentration creates a mathematical singularity where the covariance matrix becomes low rank. This matrix, known as the Hessian, determines the local geometry for steering. When rank deficiency occurs, the dual coordinate hits a boundary wall. At this point, direct steering updates in the dual space become ill-defined. This boundary wall represents a hard limit on standard gradient-based methods. The geometric path becomes fragmented and unstable within the dual space polyhedron. To overcome this limitation, a more sophisticated approach to updates is needed. This hurdle explains why simple dual space addition is insufficient for all scenarios. Addressing this singularity is essential for maintaining robust performance during model inference. The implementation solves the rank deficiency hurdle through regularized Newton updates. The algorithm's base function traces the nonlinear primal path. This path corresponds to the linear steering occurring in the dual space. The core update equation uses a specific regularization parameter. Alpha is set to 5 times 10 to the negative third power. This value is added to the identity matrix multiplied by the covariance. The system then solves for the update vector v against the steering vector beta w. This nudge pushes the distribution toward higher entropy states. This move allows the system to escape the boundary wall of the dual space. By increasing local variance, the update successfully recovers mathematical rank. This process ensures that the steering remains stable even under extreme token concentration. It converts a theoretical dual path into a viable engineering implementation. Dynamic trajectory alignment highlights the efficiency differences between dual and Euclidean steering. Researchers track the cosine similarity between update steps and the target concept vector beta W. The metric measures how effectively the steering path aligns with its intended direction. Dual steering efficiently maintains high cosine similarity values throughout the entire steering process. It successfully slides along the boundary of the convex hull of the dual space. In contrast, Euclidean steering fails to maintain proper alignment as target probability increases. This failure forces the steering path through irrelevant interior probability space. This misalignment is clearly visible as Euclidean similarity values collapse. Meanwhile, orange and red lines for dual steering remain elevated on the plot. These findings demonstrate that dual coordinates provide a more direct path to concept manipulation. The superior alignment ensures higher precision and reduces energy wasted on off-target shifts. Performance validation of dual steering focuses on two major open-source architectures. For the large language model benchmark, the researchers used Gemma 3.4b. Context embeddings for this phase were sourced from the Allen AI C4 dataset. This provides a robust and diverse baseline for testing text-based concept steering. For the vision language architecture, the team utilized CLIP 2. This benchmark combines vocabulary and embeddings from synthetic objects and Microsoft Cocoa. Using these industry-standard models ensures that results are representative of modern AI capabilities. This cross-modal setup demonstrates that information geometry is a universal property. It applies equally to token generation in LLMs and visual embeddings in CLIP. These rigorous benchmarks provide a foundation for the empirical comparisons that follow. Off-target preservation metrics show a massive performance gap between dual and Euclidean steering. Researchers measured the KL divergence of distributions that should remain neutral during steering. In this analysis, a lower value indicates superior preservation of unrelated model concepts. When the target concept probability reaches 100%, Euclidean steering suffers catastrophic degradation. This failure is visible as a sharp spike in teal lines for LLM and CLIP benchmarks. In contrast, the orange lines representing dual steering remain remarkably flat and low. Dual steering successfully maintains near-zero divergence even at maximum concept influence. This performance holds across multiple diverse benchmarks, including synthetic objects and Cocoa. These results suggest that standard steering methods fundamentally corrupt model knowledge. By respecting the underlying information geometry, dual steering achieves near-perfect isolation. This isolation is critical for any production-level application requiring safe model steering. Component ranking stability provides further evidence of the structural integrity of dual steering. The researchers measured this stability using a weighted sum of inverse rank differences. Standard steering methods frequently scramble the internal ranking of off-target semantic concepts. This disruption occurs even when overall KL divergence might seem relatively low. This ranking shift is visualized through noisy spikes in teal lines across 12 diverse tasks. These tasks include translation and color changes, representing a broad range of model behaviors. In stark contrast, dual steering keeps the fundamental order of off-target tokens completely intact. The orange lines representing dual steering stay consistently flat at 0 for every task. This preservation confirms that dual steering operates as a truly isolated concept operator. By maintaining semantic ranking, dual steering ensures the model's underlying knowledge remains coherent. This level of stability is essential for maintaining trust in large-scale model steering. Visualizing token probabilities provides clear proof of zero collateral leakage with dual steering. The researchers tested steering from a base context to a third-person context. In this test, the base token maintain is steered toward the target token maintains. In standard Euclidean steering, massive probability mass leaks into completely unrelated tokens. This phenomenon is clearly visible as large green and purple areas in the top chart. For example, a significant amount of probability is unintentionally transferred to the word to. In contrast, the dual steering architecture shows a direct and isolated mass transfer. Probability shifts cleanly from the light blue base token to the dark blue target token. The resulting chart exhibits a smooth transition without any collateral leakage. This visual evidence confirms that dual steering operates with surgeon-like precision. By isolating concept changes, the system preserves the integrity of the original context. This breakthrough enables reliable steering for sensitive language tasks. Vision language manipulation provides further visual proof of the precision of dual steering. The researchers tested the steering of a cat concept toward a dog concept using CLIP 2. In this task, the goal is a clean transition between two distinct object categories. Standard Euclidean steering unintentionally promotes off-target cat and dog compositions. This results in the generation of hybrid animals with cat heads and dog bodies. The top row of images clearly demonstrates this loss of semantic object boundaries. In contrast, the dual steering architecture directly shifts probability to the intended dog targets. It flawlessly preserves distinct object boundaries throughout the entire transition. The bottom row shows clear and non-hybrid dogs as probability mass increases. This evidence confirms that dual steering maintains the integrity of high-level visual concepts. By avoiding hybrid distortions, the system ensures more reliable vision-to-language interactions. This breakthrough is critical for building accurate and robust multimodal AI applications. The research concludes that the assumption of flat representation space in AI models is now obsolete. Large neural networks do not operate within a simple Euclidean geometry. Information geometry instead aligns mathematical control with the intrinsic behavior of the model. Dual steering establishes a new standard for robust and zero-leakage interpretability. The system achieves near-perfect isolation of concepts across language and vision benchmarks. This precision prevents the catastrophic off-target effects observed in standard linear methods. One remaining boundary involves managing rank deficiency during periods of high token concentration. This work provides a scalable path for precise and safe concept manipulation. The researchers have released a full implementation as an open-source project. The code is available at github.com/kehopark/dual steering. This breakthrough marks a definitive shift toward geometrically grounded and transparent AI.